Hello, math humans. We're going to do P2 today. We're going to be talking about linear models and rates of change. Our objectives are that we're going to calculate the slope of a line, we're going to write linear equations, and then we're going to interpret slope as a ratio or rate. Also remember that we are still in review mode, and that means that we have a ton of little sections that we're going to cover. The first thing we want to talk about is slope. And remember that slope is the change in vertical over the change in horizontal. And that means it is delta y over delta x, which means it's y2 minus y1 over x2 minus x1. Okay? Slope is also called a rate of change. Okay? If I have parallel lines, so if I have parallel lines, then the slope of the first line is equal to the slope of the second line. If I have perpendicular lines, that's an L, woo, writing is optional today, then that means that when I multiply the two slopes together, I get a -1. So for example, if I had M1 is 1/2 and M2 is a -2, then when I multiply those two guys together, I would get a -1. So perpendicular lines have negative reciprocal slopes. If I have a vertical line, the slope is undefined. And if you'll look back at our formula, that's because if I have a vertical line, right, so all of my x's are the same, so if I subtract, then the difference is going to be 0, and then the world explodes. So the slope of a vertical line is undefined, and then if I have a horizontal line, then the slope is equal to 0, and that would be this guy. And if you think about that again in terms of our formula, that means that the y values aren't changing, and that means that the slope of a horizontal line is 0. All right. Before we do our next example, I want to write the point slope formula of a line. And this is going to be your best friend this year. And remember that is y minus y1 is equal to m times x minus x1. And in calculus, one of the things that you will be told throughout the semester is that we often get in trouble when we reduce things. So for calculus, we use this formula almost exclusively to write the equation of a line. And then when we report, we can also report in point slope formula as well. So we will talk about that as we move along. So for our first example, I want to write a linear equation for a line that has slope of 3, and then it passes through the point 1, -2. The reason that point slope is so handy is that I don't have to solve for the y-intercept, which is what most of us screw up when we're doing the slope-intercept form because we make math mistakes. Point slope is significantly easier. So I always rewrite my equation when I use it so that I make less mistakes. Now I just need to substitute in all of my numbers. So I get y plus 2, a negative and a negative is a positive, is equal to a slope of 3 times x minus 1. Now I am okay if you report your answer this way. I am also okay, and that hurts me a little bit, and so I tend to leave my answers like that, and then that would be my equation. And then we are done. That was pretty straightforward. All right, so the thing that we want to talk about slope now is kind of about the units. So I'm going to write that we're going to talk about the units of slope. So slope is often considered a rate of change, and you'll see ROC. And so if I think about delta y over delta x, the equation tells you what the units should be. So let's say that I have a change in volume over a change in time, and I ran out of room, so let me go to the next page. So then my units would be a volume unit, so let's say it's meters cubed over a time unit, which would be maybe seconds. So the cool thing about a slope formula, delta y over delta x, is that it tells you what the units are going to be. So one of the things in calculus that is very important is to always include the units if they're given, because oftentimes on an FRQ you will get a point just for having the correct units. And so we really have to make sure that we are paying attention to that lovely little detail. All right, for example 2, I have a little bit of writing to do. We have that the population of Colorado was 3,827,000 in 1995. And remember, our book is old, so our data is old. And it was 4,665,000 in the year 2005. The question says, over the 10-year period, what was the average rate of change? And that's our task. So the average rate of change, AROC, is AROC is equal to the average rate of change. Gotta love math symbols. So it's still just going to be delta y over delta x, but I'm going to take my data. So I had 1995, and because I can't change time, so that's my dependent variable, and 3827123, and so that's a data point. And then in 2005, I had 4665123. I always like to put my data into ordered pair notation because then I typically make less mistakes. The average rate of change is just delta y over delta x, so it's going to be 4665123 minus 3827123 over, the difference was 10, right? 2005 from 1995, and then that means that my average rate of change is equal to 83800, and remember, this is a rate of change, therefore it needs to have units, and the units are people per year from 1995 to 2005, and I'm going to use interval notation, alrighty? Because when we have an average rate of change, it's very important to note when that average rate of change happened, because over a different time period, the average rate of change could be different. Remember from our previous math courses, if I have square brackets, that means that the endpoints are included. And if I have round brackets, that means that the endpoints are not included. And I always think about these. This is a closed circle. This is an open circle because we learned that a million years ago. All right. The slope-intercept form of a line, and I'm not going to spend a lot of time on this just because you've seen this before, so I'm just going to go ahead and write it. So the slope-intercept form of a line is going to be y equals mx plus b. The primary purpose for this equation is graphing because it makes my life easy if I'm going to graph. I put the y-intercept, 2 points define a line. I put the slope on the graph, and I can connect the dots. So oftentimes we use this form for graphing. Sometimes we use it for reporting. It depends on the situation and what you are asked to do. The next form of a line is called the general form, And it's a little bit more unusual, and again, you should have seen it, and this is of a line. And I skipped an example because I just think that I don't need to go back over. So my numbers are going to be a little bit off. This is the general form of a line. I'm sorry, I look like I'm scribbling today. Things to notice about this is that everything is on the left. There's nothing on the right. Okay. A has to be positive and a whole number. So if it's not, then you can manipulate the equation to make sure that you get to that point. All right, so I'm going to go, just to keep consistent with my notes, I'm going to call this example 4, even though it's really our third example. That way I don't get confused if you ask me questions. So this one says, find the general form of the line that passes through the point 2, -1, and is perpendicular to 2x minus 3y is equal to 5. So if we talk about what we've been given, we want to write the equation in general form, so in this form, and we've been given the line that it's perpendicular to in the same form. Now notice that the 5 is on the other side, so sometimes they do that. Technically, it needs to be on the left-hand side if it were in general form. So as I start this equation, the first thing that I want to do is I'm going to take the 2x minus 3y is equal to 5, and I'm going to put it in slope-intercept form. So I have a -3y is equal to 5 minus 2x, and then I get y is equal to 5 minus 2x divided by a -3, and I'm going to write this as 2/3 x minus 5/3. All right, so that is the equation in slope-intercept form, and the reason that's important is to find that initial slope. So the slope that is initial is 2/3, so that means my perpendicular slope is going to be a -3/2. And then I'm going to use the point slope formula, so y minus y1 is m times x minus x1. Remember that the point that the function goes through, or the line goes through, is 2, -1. Excuse me. So now as I write my equation, I get y plus 1 is equal to my slope of a -3/2 times x minus 2. And I could stop there. I'm just going to take this guy to the other side, -3/2 x minus 2, and then subtract 1. And then that would be, oops, I lied. So we do need to fix it because it said we needed this in standard form. So I'm going to go ahead and distribute, and my bad, I'm going to go back to here. So y plus 1 is equal to a -3/2 x, and then plus the 2's cancel, so I get 3. Remember, everything needs to move to the left, and so I'm going to get 3/2 x plus y. 1 minus 3 is a -2 is equal to 0. We talked about a has to be positive and whole, so I am going to kill the denominator. So I'm going to multiply both sides of the equation by 2, and I get 3x plus 2y minus 4 is equal to 0, and then this would be in general form. All right, remember, kill the denominator is lovely because it makes our math simpler. The next thing that I just want to remind you is about some grapher settings. Okay, so there's a couple of things that you need to remember. They're very handy. Zoom 6, I'll put Zoom 6. This is your standard viewing window. Okay, and that should be the default for most things. The other one that I use a lot is Zoom 7, which is a zoom trig. Okay. The other one that we can use would be your Zoom, oops, that's an O and an M. Zoom 3 means I'm going to zoom out, and then I could do a Zoom 2, which is the box, and occasionally that is helpful if you have a particular portion of a graph that you're trying to use. Okay, And I think that's it. The only other one would be a Zoom 9, and that is Zoom Statistics. And this is what you use for regression. I will tell you, there are very, very few times when you are allowed to do regression analysis in calculus. So though this is a good tool to have in your toolbox, it is something that we don't get to do very often in calculus because they want you to do math instead of just push buttons on your calculator. So our next example, example 5, and let me check real quick, it is our last one. I want to find an equation of a line tangent to the circle. So this is kind of a cool problem. And the circle is going to be x minus 1 squared plus y minus 1 squared is 25 at the point 4, -3. So you think this is actually really nice to draw a picture so that you can see what's going on. So if you remember, my vertex of the circle, this is the equation of a circle, is going to be hk. So that means my vertex is going to be 1, 1. My radius is going to be the square root of r squared. So my radius is 5 because this is the radius when I take the square root of that. So now I'm going to draw my circle. So my circle is centered at 1, 1. And then it has a radius of 5. And I'm just going to give myself some guidelines so I don't make a horribly pathetic graph. So if this is my center, then 1, 2, 3, 4, 5, my circle is going to look kind of like this. Okay? And so that would be my radius of 5. It's going to go through the point. So this is 1, 2, 3, 4, and then 1, 2, 3. In theory, that's 4, -3. And I want to write the line that is tangent to that point. So that's kind of cool. One of the things, and it's a crappy picture, so I'm just going to apologize right now. If I go from the point of tangency on a circle back to the center, this is going to be a perpendicular line. And so this is 4, -3. Okay, and in theory, that's something you learned a million years ago in geometry. So I am looking for the slope of the line from the center to the point of tangency. Okay, so that's going to be delta y over delta x, and I'm going to write the coordinates of this guy up there so we can see it. So it's going to be a -3 minus 1 over 4 minus 1, so it's going to be a -4 thirds. And that is the slope of this line that we drew, the radius. Okay, so then the slope of the tangent, because when I have a tangent to a circle at a point and I draw the radius, this is perpendicular, so the slope of the tangent line is going to be 3/4. So that's actually pretty easy. So it looks like a complicated problem, but it's really pretty simple. So now I'm ready. I have the slope of the tangent, and I know my point that I want my line to go through, so I'm going to do my point slope formula, m times x minus x1. So it's going to be y plus 3 is equal to my tangent slope times x minus 4. And then I'm going to write y tangent, so I know that I'm reporting the equation of the tangent line is 3/4 times x minus 4 and then minus 3. Now, if I had to do additional math on this equation, then I would simplify it. But if this is all I have to report, I would stop here, all done. All right, my dears, that is it for today. I will see you soon.